So in this next part, I want to talk about the modeling framework, which is called Markov decision processes. We're going to talk about the interaction loop, the modeling framework, and then we'll also actually present the earlier ride-sharing example in this framework. And we'll also talk about some of the challenges that come up, for instance, exploration versus exploitation. So it's the one conceptual way to think about sequential decision making is that we have an agent, and this agent is interacting with the environment. So I'm going to introduce a couple of the characters here. You can view this as a reference for a notation that we will use in this unit. So the agent will make an observation from the environment, as well as a sense of how good is this state, is the situation, okay, or is this observation? And that's the reward signal. And based on this observation and reward, the agent will try to improve its situation. So it'll try to make good decisions based on this. So it will, sort of given an observation, it will issue an action. This action will affect the environment. The environment will then transition to the next state, and then the agent will receive a subset of that state, which is an observation. Okay, so a couple pieces of notation. First, I should say the goal of the agent is to maximize the reward over time, not just the one-step reward. That would be the non-sequential problem. We are interested in the reward over time. This is often called the return or the cumulative reward. Okay, and now I'm overlaying the slide with the notation. So S for the state, O for the observation. In this, for this unit, and oftentimes in the literature, folks will be a little bit sloppy and interchange the state and the observation. And we will mostly do that as well. So we will mostly refer to the state, and we will typically mean the observation. So just be aware of that. So R often denotes the reward term. Pi often denotes the policy, or basically the mapping from the state or observation to the action. Okay. The pi prime often denotes an update to the policy pi. And then we'll denote the transition in one of two ways. It can either be denoted in terms of a transition function, which would take in a state and action and give the next state, or a probability function, probability matrix, which will take in a state and action and give the probability of transitioning to a new state. Okay, so it's like a cube. Okay, good. So let's talk about the order here is a little mixed. Okay, so we're going to first talk about the Markov decision process. And the Markov decision process is actually a subset of this picture. I've outlined it here. So notably it excludes the agent. So it's mostly the interface with the environment. Okay, so the agent will interact ultimately with this Markov decision process. So ultimately, we're going to try to optimize this Markov decision process, which really means coming up with a good agent. Just keep that in mind. But first, we're going to break down this Markov decision process. And we're going to do this by looking at a particular example. Oh, and I should note, we're going to, for now, assume finite horizon problems. This means, okay, so we'll use the notation T for the horizon, and this is going to be finite. What this means is that we're not going to, when we say we care about the reward over time, we care about it over a finite number of steps. So you can imagine for the rideshare example, we care about this for the shift of the driver. We don't care about this for all of eternity, okay? Okay. So yeah, and later we're going to talk about infinite horizon problems, mostly because there are really nice algorithms that result, and so it's good to understand how those come about. So let's talk about the Markov decision process in the context of an example. So here's an example of the amazing goods company. And here's a diagram that depicts what's going on. We have an inventory system. Okay, you can think of this as, we're going to think about only one type of item. Okay, so it's perhaps different from a particular company that you might be thinking of. So just one type of item. Every month, there's some demand for that item. And there is some amount of stock in the inventory. And every month, the manager, can order some more stock, and there is some reward associated with, say, the sales, the storage costs, and so on. Okay, so let's walk through this in a bit more detail. At each month T, a warehouse contains ST items of a specific good, and the demand for that good is D, and this could be random. At the end of each month, the manager of the warehouse can order A sub T more items from the supplier. So there are some factors to consider in this problem. There's a cost to maintaining an inventory of size S, that's denoted by this function, h of s. There's a cost to order the items, of course. There is some income from selling the items. Let's say we sell Q items. And if the demand is greater than the available inventory, then, well, we can't sell more items than we have, so customers will leave. And there's some value of the remaining inventory at the end of the year. Oh, and one more, there's a constraint, which is that the store has some maximum capacity, C. So what we're going to try to do is we're going to take this example and we're going to try to formulate this in the framework of a Markov decision process. And this is important because this is a lot of what we want to do in transportation, is take a problem and, again, recognize that it is a sequential problem, and how do we cast it into this framework of MDPs. So let me first remind you of one of the later topics that we touched on in Unit 2, which is Markov chains. And Markov decision processes, MDPs, are highly related. If you recall, in the Markov chain, we have a state space, S, and the system is called Markov if it has this Markov property, which is that the next state, given the history, is equal to the next state given the current state. As in, given the current state, we don't need any additional information about the past. Okay, so this was true, if you recall, in Unit 2 for the Poisson process, okay, and the MMC queues. Good. So that means that for a given initial state, we can specify a transition probability. The transition probability just needs to include the information about the current state and the next state. And that's going to be enough to specify the probability of transitioning to the next state, to the next state, to the next state. We do not have to carry around more information than the current state. The current state is sufficient to determine the probability of the next state. So this is going to be carried over to the Markov decision process. And the key difference is that with a Markov chain, we don't have any decisions to make. We don't have any way to optimize the system. With MDPs, we're going to add that degree of freedom where we can start to optimize the system. Okay, so similar idea, the Markov decision process carries around a bunch of items. This came up in the notation slide before. So S is the state space. In the example of the amazing goods company, the state space would be anywhere from 0 to C. This would be, say, the number of items in stock, okay, of that particular kind of item. C, because we have a capacity in the inventory of size C. And 0, because we can't have 0 and not, say, a negative value because we cannot have negative goods. The actions, again, this is what's new about the MDP. This is as specified by the problem. This is going to be so the action space will be the number of the stock to purchase in this month. So here we can see that the action space can actually be a function. So that here the number of items that can be purchased depends on the current state. We can order up to the number of items that would bring us to the capacity of the store C. So our action space is between 0 and C minus S. Okay, next one is the transition probabilities. This is where the Markovian assumption comes in, and there's a slight difference. Instead of the transition probabilities being just relying on the state and next state, we also will condition on the action. Okay, there are two forms of to write this. They're equivalent, and sometimes the problem will be easier to specify in one or the other, which is why I'm including both of them. So sometimes it'll be easier to write down the probability of the next state given the current state and the action. Sometimes it'll be easier to write down directly what the next state will be given the current state and action and some random variable that specifies some randomness in the system. Okay, so oftentimes, especially when the system is non-random, so we don't need to carry around this W sub t, the transition equation will be more natural to model the system than this transition probability. Good. Okay, so the transition probability or transition equation for this problem is more natural in this transition equation form. So the next state can be written as the current stock plus what we order minus what demand there was, and it must be non-negative. Okay, so we cannot go into a negative stock. Where we recall that the demand may be stochastic and time independent. Okay, good. The reward, this is a really important piece because this specifies what we are trying to optimize. So here the reward function is that combination of those multiple costs and sort of profits that was specified in the problem, corresponding to a purchasing cost, a cost of excess storage, and a reward for fulfilling orders. Okay, last but not least is the horizon. I did use the notation T earlier, so apologies for that. Sometimes we'll use H for horizon, sometimes we'll use T for, say, the number of time steps. So here we are specifying that the horizon of the problem is, say, 1 year. So let's say 12 months, because we're ordering stock once per month. A different way in which we specify the time is through a discount factor, gamma. So I'm introducing it here. Gamma is a number between 0 and 1. It's typically exclusive of 1, which is this notation here. And it encodes this idea from economics that $1 today is worth more than $1 tomorrow. That's the discount. And so we might use this instead of a finite horizon to model the problem, if we believe that this is true for our problem, which it often is. Okay, so then I need to talk about, this is just the problem, or this is just the sort of the decision process. This isn't the problem that we're optimizing. So what are we optimizing? This is the objective, often written down as follows, as this function v, which takes in an initial state, perhaps an initial action, and it tries it, and it is the sum of rewards, again, rewards over time. Perhaps there is a final reward as well that we may account for. So for instance, here, the final reward may correspond to the value of the remaining inventory at the end, and this is treated a little bit differently than the per step rewards in this summation. Okay, so as a reminder, because this is really important, what does Markovian mean? Well, we can look at what non-Markovian means. In general, there are problems that are non-Markovian, and this means that the transitions could depend on a lot more information here. Okay. One piece of notation, this process generates trajectories. What is a trajectory? A trajectory is a state, action, state, action, state, action, state, action sequence. Okay, where the state is generated from this probability, this transition probability matrix or the transition equation. And the actions are what we want to solve for in sequential decision making. So here's just a summary of the analysis for that example problem. And now let's actually walk through modeling the real-time rideshare matching problem as an MDP. So if you'd like, you can pause the video and think about it for a moment before continuing. Okay, so just to remind you, what we're doing in this problem is we are determining the we're going to determine for each driver the state, action, reward, transition, horizon for this rideshare matching problem. Okay, so this is not something that you would know. This is from the paper, and this is not necessarily obvious, but you can think about what you would have come up with. So for each driver, the state of the system might be the location of the driver, the time, say the time of day or the time of week, as well as the vehicle type of the idle driver. The action would be the request destination, location, or time. And then the reward would be, well, what would be, say, the profit or the satisfaction of completing that request? And it would be 0 if the request is not accepted. The time step, this is not, we didn't really discuss this, but this was in the paper, so I wanted to include it for completeness. The time step is actually going to be the full trip time, or 4 seconds if we don't if we don't accept this request. The transition matrix is going to be the new idle state of the driver given the request. So the driver accepts the request, then the driver in the next time step will be at the destination of that request. And otherwise, the driver will be roughly where he or she was before the request. The horizon is, let's say, infinite, but we're going to use a discount factor. And this is oftentimes how we use the discount factor. This 0.9992 is roughly a half-life of roughly 1 hour using a 4-second time step. Okay, so the analysis is here, where this is gamma to the number of time steps, seconds, divided by 4-second steps. This is roughly 0.5. And so this is roughly saying that We care about what happens in the next half hour, twice as much as what we care about what happens in the half hour after that. So there are some initial challenges that immediately appear, and this is a lot of what we're going to talk about addressing in this unit, which is if we think about these states, this actually already results in huge state spaces. This is a key challenge in reinforcement learning. So let me give you a sense of how we might encode this state space. In principle, basically every location, time, vehicle type combination is going to be unique for almost every ride, because say GPS locations are continuous. So what these folks do is they encode the location as sort of discrete. So they're binning these into categories using this geohash measure. So there are some 1,600 different options for the precise location, perhaps 50 options for less precise information. So they're getting information about the precise as well as neighborhood level location of the driver. They're also going to encode time in terms of hour of the week and not the exact, millisecond, as well as some vehicle type. So this is already a really, really large combination. This means that the state space, if I multiply this out, is about 54 million. To give you a sense of scale, the Bay Area, which is where this study was done, the population is around 8 million. So a naive approach to say collect enough data would need everyone in the Bay Area to take at least 7 rides. This is not a good thing, especially for a business to need to say take years to collect this data before you can have a viable product. So that's a lot of what motivates reinforcement learning as well. We cannot only say explore to understand, for each combination of state location, vehicle type, what would be a good action to take. We also cannot only exploit, which means we cannot just take what we think is going to be the best decision because we don't have necessarily the data to do so. So a lot of what comes up in reinforcement learning is how do you trade off exploration and exploitation to consider some states, collect some data, determine what actions are good. How do you collect the right data? How do you make the right interactions? How do you make the right decisions so that over time your algorithm can make good decisions in the future?